Next topic I wanted to cover today is what's called range tomography. So we saw ray tomography and its how it works and like some of its uses. So the next basic idea is what's called range tomography. And so here is an illustration of the kind of what you can do with this approach. So we are assuming that there is an object in 3D somewhere deep inside which we are interested in figuring out the location of. Okay, so it's at a location at position R or X, Y, Z, and what we will do is send a signal from one of these. We have a source and a sensor combined into one like entity. We send a signal and get a signal back. Okay, and at location R1, then have a sensor and source and sensor here at R2. We send and get back the signal, and location R3 send a signal, get back the signal, and so basically we'll do this at a few different locations, and we can figure like so if we just have one point and say three different locations, then through a process of triangulation, you can figure out where the object is, right? So let's say this, you measure like for now, let's say you send a signal, it takes some time to come back. You have to measure, like you know what time you sent it, send the signal, you know what time the signal comes back. So using the time measurement, you can perhaps measure distance R1 and then you know the location R2. You send a signal, you and get it back. You measure the distance capital R2. You then measure the distance capital R3. So if you know the positions here, and you know R1, R2, R3, then you can you can actually back calculate where the position is, right? So in essence, this is the basic concept behind ray tomography. Okay, so range tomography. So in these kind of systems, of course, you will not have one scatterer alone, and you will not have kind of just three sensors alone. And so the question is like when you have a large number of scatterers, and then how do you make measurements, and how do you take the data, how do you use that data to figure out what is inside. So that's the next thing I'll discuss. But the principle is like some kind of triangulation equivalent. We will not actually calculate like do triangulation, but something which is equivalent to triangulation. So here is one kind of a one approach to doing this. Let's say you have one probe, so which is all like so. It sends out. Let's say there are instead of one object or one sensor inside. Is the screen blinking? Is not left. Okay. I'm not sure. Sorry. Yeah. Okay. Yeah, so if we have instead of one scatter, if we have four of them as shown here. So now, so if you send a signal, so if this is also like it sends a signal, wave, and then it also gets back a wave. Like it also has a sensor. It's a probe and sensor as well. So now, if you think of all the different like waves, like look at the distance of different objects to this particular probe, then you can see like uh, if you make a measurement as a function of time, you will see that you will get as like the signal at 1 and signal at 2 and 3 because they are on the same circle. So you will get both the values, both the signals at the exact same time, right? Like the wave takes the same amount of time to go and come back because they are equal distance. So you cannot distinguish 2 and 3 from this kind of a measurement. You can distinguish 1 and 2 or 1 and 3 and 1 and 4. So, but you cannot distinguish 2 and 3. And again, 4 because it's farther away. you'll get it at a later time. So one measurement will give you some amount of data, but it cannot uniquely distinguish. One measurement is not enough to uniquely distinguish all the different points. So the basic idea is move it to a different point. So if you move the sensor to a slightly different location and do the same kind of experiment, then again you send out waves in all different directions. Then you will get a signal from 2, and then you will get a signal from 4, and you will get a signal from 1. But because this 3 is very far away, you may not even get any signal. The signal may be too weak. As you go farther away from the sensor, things may kind of decay, or things may become a bit attenuated, and so you will not. So you get another data set. So you also have to account for the possibility that not only that there are 4 points, there could in your measurement there could actually be sometimes 3, sometimes 4. So a variable number of points as well. But once you get this data, you can somehow go from the data to the structure of this particular object. So that's basically yeah. So that's yeah. Mhm. It can be integrated into one entity. So to give you a different example, like you could have say an optical fiber. Light comes out of the fiber, falls on the object. Whatever scatters back could be collected from the same fiber. So you put a lens. So let's say you have optical fiber. Light comes out of this. Put a lens and it focuses here, right? So if let's say light scatters back, it goes through the same lens and goes back into the fiber, right? Mm-hmm, mm-hmm, mm-hmm. Yeah, so if the forward going way will if one is coming out, the other is going back in. So, so that's an interesting question. There has to be some mechanism by which you separate out what is coming in and what is going out. So one way to there is a few different ways of doing it. In the case of optics, so what you can do is have light coming in, use what's called a beam splitter. Okay, so this sends half the light here, half the light here. So you lose half the light. The disadvantage of this approach is that you lose half the light, but let me give you an example of how this can possibly work. Okay, so this light goes to, let's say this falls on the sample, it goes to a fiber, whatever happens. Then the the light comes back. I'm using different color, but it's the same wavelength that comes back. Okay, now it reflects this way and it also transmits. Okay, what goes back you don't care about. You put a detector here, so the light that goes this way, you can put a detector here and measure. So this is one way in which you can separate out the light that comes back from the light that's going forward. Okay, there are a few other different, there are what you call circulators, there are different kinds of devices which approaches to basically making the separating out light coming in and light going out. Yeah, sure. So that depends on the properties of the scatter. So you could have highly scattering object, not just a small object, an extended object that may, it's not a perfect dot, it's like an oval shaped thing. It could scatter like so, depending on the material properties, object properties, you could have different kinds of shapes and that kind of. So that's yeah, uh, yeah, like it's the ideal situation is perfect dot, right? But in the realistic scenario, it is very different. Any other questions? Sorry? No, so the lines here are drawn to just illustrate equal distance. Like if you cross, if you take this, uh, if you take this point as the center and draw circles, right? Any point on the circle is equal distance to the center. So that's why that is what these lines illustrate. Okay, that's the goal of this illustration. Okay. Yeah, this is the first slide after the break. Huh? So what is one? What do you mm-hmm. Something of this sort? Sure. Mm-hmm. Mm-hmm. So basically, that's a non-trivial problem, and there are if you make some assumptions about the nature of the of like so based on different assumptions, you could kind of fill things in. So in fact, this is something I'll talk about in the next kind of class. So you could do like so there are different ways of estimating the kind of out what is outside, and different based on different assumptions, you could get different answers. The question is how close will you get to the real? So there is it's like some kind of interpolation. Just like you could do linear interpolation, line interpolation, you can do different kinds of things. So in a particular scenario, what is the kind of optimal, depending on your model for the measurement and model for the object, you could have different answers which are reasonable. They are around reasonable estimates. It will come close is what we are saying. It's still not perfect, but it will come close. Okay. So yeah. So this kind of an approach. So what happens? So in range tomography, one of the kind of underlying assumptions here is that so if you have a scatter at a position r, and this rs is the location of the source, then this distance is twice this r is basically r to s and rs to r and r to rs back, right? So twice that distance is velocity times that. So if you know this, not velocity, speed of say, a wave in the like that goes, and if you measure if you know the speed, if you measure the time, then you can estimate the distance, for example. Okay, and so these kind of measurements are used in several different there are several different imaging systems that use this kind of an approach, and on a larger scale, one imaging system is called what's called synthetic aperture radar. Okay, so this was invented a while ago, where the basic idea is in an airplane you can uh, keep getting this radar information like kind of echoes, send a signal pulse back and measure time that comes back and make measurements of for the object. And in fact, you can after doing some inverse calculations, you can get the three-dimensional structure of buildings and kind of on the ground instead of getting a photo, instead of getting a photograph of the surface. Let's say if a plane is you are in a plane, airplane, and basically you see down and you can take a picture with your phone, right? But with this kind of an approach, you don't just get 2D, you make multiple measurements as you're flying. From essentially, people into looking at it from different angles, and you can get a three-dimensional topology of the ground instead of the 2D picture that you get just from a photograph. So in fact, like some of you might have seen on Google Maps or Apple Maps or things of that sort. Sometimes you have 3D structure of cities or buildings and things like that. Right? So there are different ways of actually doing that. Different companies or different people use different approaches. One approach is something of this sort. You take multiple aerial pictures and doing this synthetic aperture radar calculation it is a three-dimensional structure of objects. Many of you might have already. How many of you have seen that 3D on Google Maps, like topological kind of? If you have wondered how they actually do that, they use this kind of an approach. So this is on a big scale, but you can also build imaging systems on a microscopic scale which do the same kind of thing. Okay, I'll talk about how we can, this idea of synthetic aperture radar is useful in optical coherence tomography or medical imaging kind of approach in a different lecture, but it also has big, large scale, bigger scale and smaller scale applications. Okay. So, yes. Yes, yeah, sure, absolutely. So yeah, so in range tomography, instead of having the source and the sensor at the same location, an alternative is you can have them separated out. In this case, what like it's a little bit more complicated, but it has some advantages as well. So in this case, the source sends like a signal, like a wave out, and then it goes to the this like it travels a certain distance and gets to the sensor. And in this case, this distance plus distance is equal to, if you measure the time and you know the velocity, the sum of the distances is what you will know, right? And does anyone know, like, if sum of two distances is a constant, what kind of a curve this will be? Sorry? Yes, it's ellipse, right? If these are the foci of the ellipse, and if you take a line and the locus of points which have like sum of distance is constant is an ellipse. So in this case, the previous case is a circle. In this case, it's an ellipse. So every point on that ellipse will give you the same data. So you have to, therefore, you can move the sensor to multiple different locations. You just can't use one measurement. You have to use multiple measurements, and these will be a bunch of ellipses. And so by you can kind of like measure the time intervals of at which you get back at every different sensor and reconstruct using the time reversal, and you get back to a three-dimensional structure from the inside. Okay, so by making these bunch of measurements, you can do the inversion. So this is kind of so you the time like so in this case, if you have this like R like RS, which is the source, and RT, which is the detector, and there's a point R. So the time it takes from RS to RD, and if there's a point scattered at the location RS, it's R minus RS divided by speed, because the time it takes to go to the to R, and then time it takes to go back to the detector. So the sum of the two like times is the overall time, and the data you measure going from RS to RD. So basically, for a pair of sensor and detector, you will get a time measurement. So that's illustrated. So this is the kind of data you could measure at different sensors. So the equation for that kind of a measurement will be, so like the FR is the structure of the object, and it gets multiplied by the structure of the how the imaging system operates, the nature of how the wave travels and comes back. The H captures everything about the how how much time it takes for the wave to travel and come back. And by that kind of doing some inversion, you can reconstruct the 3D structure from the data. So that's the basic idea behind this. This is the concept of range tomography. Okay. So, any questions? Okay. So the next important topic I wanted to discuss today is what's called wave tomography, and it's also called diffraction tomography. And so this is a, it's typically used for light, and it is a fairly it's a good way of measuring things which not only uh, absorb but also scatter light or diffract light. Okay, so in the ray tomography, what we assumed was a light ray goes through the object in a straight line. There is some absorption as it goes along, and one ray goes to the one source, emits a ray, and it goes to a detector, right? That was a straight line. Now, instead of that, if a wave comes in and diffracts in all different directions, right? The object diffracts light, and the wave that comes in, let's say the wave that comes in is a plane wave, and a plane wave comes in and it becomes multiple plane waves and goes in all different directions because of diffraction, and you get a detector and you measure the detection. And so it's a much more complicated process than the ray version. But people have figured out how to do the inverse reconstruction for this kind of an approach as well. And this is especially useful in optics, where you're looking at small objects, where the object is of the same, or the entities inside the object are of the order of the wavelength of light, right? Like whenever you have objects which are close to the wavelength of light, there is diffraction and there is scattering, and therefore that's when it becomes that's when these kind of approaches are useful. And so that's the next important thing I'll discuss today. Okay. So the basic idea is we have a source of light which comes. There's a 3D object which is f x y z. Okay. So it's a function of x y z, and this tells you f of x y z tells you the internal structure of the object, and light comes from one direction, and after it goes diffraction, it falls on a sensor or a camera sensor, say, then it gives to an image GP of x comma y. Okay, and then that is one image that you get. Then you change the view, change the angle at which light comes in, and it goes through again, like the sensor on the other side again makes the measurement. You keep making this bunch of measurements. The question is, in this case, even though it's a complicated interaction, one point gives you many points. Previously, it was one-to-one functions. Now it's one-to-many kind of interaction. In that case, how do we put the data together in such a way that you can kind of do a 3D reconstruction and identify the structure of the inside of the object? Okay, that's the next thing. Say that again. So it could, so the light, so this is commonly used for light, with near infrared, infrared light, like of the order of 1 micron wavelength, like a ballpark, I'm saying. So something like this. You could use it for any wavelength. There is the principles can be used for any wavelength, but in terms of if the objects are microscopic, then it's typically so visible light is about 420 to 650 nanometers ballpark. Okay, and then 650 all the way to about 2 microns is infrared, near infrared, and 2 to 12 is about mid infrared, and 12 beyond 12 is approximately as far infrared as well. So those are the wavelength ranges in which this is commonly used. And does it answer your question? What is the okay? Yeah. So you could also use it for radio waves, like having very large objects and very large waves, and you could also use it for very tiny objects. You can use this with UV light, and there'll be problems with it, like multiple scattering, and there's issues that you will encounter. But the thing is, in principle, you can use it for anything. but in practice, it's used for infrared light commonly. Mm-hmm. Mm-hmm. That's an interesting question. It depends on the source of noise. So if uh, so um, sometimes, like if you want to make very sensitive measurements, it may be that you will need to do that. But to give you a sense for like when it is, let's say you're making measurements with infrared light. Okay. Now the thing is, if all the other light in your room is visible light, then you can put a cutoff filter which removes visible, and the sensor could only be sensitive to infrared. And that way you can, even though the light is on, not most of the light that reaches the detector would be infrared only, because you're using the optical filter to remove the visible part. So that way you can keep the lights on. Alternatively, you can not put that filter. Maybe your number of photons you get is too that small, and like like every photon you want, that you may have some efficiency losses, right? So in that case, you make it dark. So it depends on the how sensitive your measurement is, and so on. Okay. Any other questions? Okay. Yeah. Yeah. So here is how this idea works. Okay. So so a source of light is incident on the object, and so the data that you measure is GP of R. It depends on the object structure itself. It depends on the light incident, and it depends on how the light, the instrument collects the imaging process. Okay, how light travels and so on. So that so each captures the instrument itself. The UP is the source. The UP is the source of source of light, and F of R prime. F of R is the three-dimensional structure, three-dimensional object. So what this is, all this is saying is that the data that we collect depends on all these different parameters. Okay. So now a model for use in optics, a useful model for the object is if there are, say, uh, subtle changes in the refractive index inside the object, that may be what you are measuring. And so this k is k square minus k square, which is equivalent to ns square minus n square. So n is the refractive index of the background, and say there is a something which is has higher refractive index, scatter inside the object, and that the refractive index of that kind of object is ms. So ns square minus n square is called the scattering potential. How much of light scatters, proportional to how much light you get back when light scatters. Okay, so the object itself is defined by the variation in refractive index inside uh, like uh, the structure of the object is defined by the refractive index variation inside the object through this kind of an equation. And H here is how light propagates, right? So you are assuming that each dot, what does this, we have seen this before, what does this mean, what does this remind you of? Does anyone remember from previous classes what this equation tells you? This is not about the equation, this is something else. It is of the form e to the I P dot R divided by R. Spherical wave. Correct, exactly. So instead of R here, you have R minus R prime, which is the relative distance, right? And R minus R prime. So that's, I think, this. Okay, so what we are saying is that take a point that is a way that emits a spherical wave. Okay, so that, and you add up, when you integrate, you add up the contributions of different spherical waves. That's what gives you the detector signal. That's really all we are saying. Okay, so whenever you see the equations of this sort, it's important that like you figure out what it means. And in this case, the interpretation is, if you look at this and if you look at this, it is there are scattering objects inside the scatterers inside the object. Each scatterer will emit a spherical wave. When you integrate, the integral says to add up the contributions of all the spherical waves, and that is the detector signal. Okay, this is a detector signal. The left hand side is a summation of that all this for all the locations of scatterer. You add up the spherical waves, and that is what you get. Okay, and this UP is, so how much of the light, what is the intensity of light that scatters? It's proportional to how much of light is falling. So this says that the amount of scattering signal, the spherical wave intensity that you get is related to the amount of light that falls from what you have incident. The incident light scatters the spherical wave. Each of this, add up this contribution for all the spherical waves. That is your data. Okay, that's how you think about this kind of equation. Question? Okay. Yeah. So here is kind of another illustration of this part. So there is this what is called the radiation slice theorem, which says in this kind of a scenario, so if you have sources of light inside an object, like if the object consists of multiple dots, which are each of them are emitting light, and each of them, like, so you add up all the spherical waves from each of these dots, which are source emitters, and if it falls, and you may make a measurement here. So this is S of x comma y comma z, right? Like, so those are the source distribution of sources inside the object. So take the three-dimensional Fourier transform of this, and now you have collected data which is an image, two-dimensional, right? Image is a two-dimensional, like a plane. If you take the Fourier transform of the data, the Fourier transform of the data is basically this radiation slice theorem says is like along a curve. If you take a Fourier, if you cut a curve, cut a kind of a surface on a sphere in the Fourier transform, that is the Fourier transform of the data. So take the Fourier transform of the data, that will actually be a curve inside the three-dimensional space. So it's analogous to the projective slice theorem in ray tomography, where like a line becomes kind of a cross section, like a slice in the Fourier domain, right? So this is a three-dimensional version of that, where you take the data, take a two-dimensional Fourier transform of that will be proportional to, it's like you paste it on a curve in the 3D Fourier domain, and so that will give you one slice of data in some sense. In three-dimensional, it's a plane. It becomes a plane along the surface of a sphere. Okay, and this sphere is called the Ewald sphere. Okay, so this is honored in the name of the scientist, and so along this sphere, and the radius of the sphere is the value k. Okay, so this is the kx, ky, kz kind of a three-dimensional Fourier space, and k is here is 2 pi by lambda. That's k. So the radius of that sphere is like the magnitude of vector k, and so in the so this is the essentially the radiation slice here. So with this kind of an approach, using the same ideas that we use for inverse reconstruction of ray tomography, we do the same basic, like kind of use the same principle and do the inverse reconstruction to see the inside structure of this kind of object. First, we are assuming that each dot, there are point emitters or emitters inside. So these are sources of light inside a three-dimensional object. That's the assumption. And this, so each point is radiating uh, light and a spherical wave, and so this is the radiation slide theorem. Question? Okay. So here is the mathematical expression for the radiation slide theorem. So you take the data, take its two-dimensional Fourier transform, and take the three-dimensional object, so see a bunch of sources. This is a three-dimensional Fourier transform of the source. You multiply it by some filtering kernel, and that will give you the that is equal to the Fourier transform of your data. In this case, the filtering kernel is equal to basically it is the spherical wave operator like after e to the I kz d divided by 2j kz. So that's kz is defined here. Okay, so basically that's so that is the nature of this kind of a filter here. So remember that kz itself is a function of kx and ky, and therefore it's actually a two-dimensional function. Although it looks like a 1D signal, it's actually kx and ky is a two-dimensional kind of a filter. It's a two-dimensional filter here. So this is essentially how we do the use this to do the 3D reconstruction. Okay. So now what if the object that you are looking at is not emitting light by itself? Then what? So that's next question we will address. And the way we will do that is we have another kind of a theorem called the Fourier diffraction theorem, which is very closely related to the radiation slide theorem, or is also called the diffraction slide theorem. So basically, what we are saying is, if the object itself is not emitting light, then you have light fall on it, and light scatters, and the scattered light will become your source. That's the essential principle. So instead of light being naturally emitted from inside the object, you force light to be emitted by the object. And the way you force light to be emitted is have light fall on it, it scatters, and those will be sources of light. Okay, so that's the essence of what we will do. And so therefore, what light will fall on this object, that is given by UP of R, and so the source effectively will be UP, whatever light falls on it, times the object scattering potential, or the properties of the object. So if higher light intensity, like you have a lot of intense light fall on an object, there will be more signal that you will get. If you have a little bit of light fall on it, then you get less of a signal. But you know how much is incident, therefore you kind of you account for it like, because you have control over what light falls on the object, you can kind of choose the values of UP of R. So in other words, you can choose the shape of the wave that falls on the object. You can choose the intensity of light that falls on the object, because you have control over what is falling on the object, and you also have control over the location of the detector, the distance, and everything. So you know you have a few knowns, and what is unknown is the three-dimensional structure. So what is unknown is when you start this is FR, right? F of R, F of X, Y, Z. You don't know what that three-dimensional refractive index distribution is inside, and you figure it out by making a bunch of angles. Okay, so one common like assumption, or one thing, in fact, what you can do in practice is have a plane wave here. Now you have a choice of what kind of a light, what kind of a beam you want to fall on the object, right? So have a plane wave incident. It's the simplest form of wave that you can kind of use. And so in that kind of a situation, if you have light whose direction vector is kp, so this kp is the wave, the flow wave that you are sending onto the object. So let's assume that it's a plane wave. What's the equation for a plane wave? E to the j minus j k dot r. So in this case, k equals kp. So kp dot r is the plane wave incident on the sample, and then that times the scattering, the object function gives you sources. So now each of these dots at position r becomes a source of light. Okay, so now you have created a bunch of sources inside the three-dimensional object. Now we do the same thing as before. Okay, so now you start with, take the object which is an fx, y, z space. Take the Fourier transform of the object. Let's call it f of this qx, qy, qz. The Fourier domain variables for x, y, z. And so this will be the vector f of capital Q, capital F of Q. Okay. So this is the Fourier transform of the object you are trying to measure. If you take the bunch of sources, so now this is what the using the radiation size theorem. So you can figure like this. You can relate this to the Fourier transform of the object. So that is what the diffraction size theorem says, that S of k equals f of k minus kp. So this is the essence of the diffraction size theorem. Okay, let me show you how this would work. Okay, so in this with this kind of an approach, you have a direction, light falling at direction kp. You make a measurement over here. Now take the two-dimensional Fourier transform of the data. You get g of kx dy. So you get a 2D image of the curve. Now you take this, put it into the Fourier plane of kx, ky, kz of the object. Okay, and then have another. So this is for one direction kp. Kp is the direction vector. It has to one direction. Now for another direction, make a second, you have a slightly different direction come in and make another measurement. Then you make another measurement at a different time, and so on and so on. Okay. So for every one of this, you take the 2D Fourier transform. You will put it in the Fourier space in like this. You will fill in the Fourier space through these curves, in fact surfaces. And if you can imagine the space is like sort of on a sphere, you have a surface, another surface, another surface, another surface, and so on. So by pasting this at multiple surfaces, you will be able to get these different for different values of kp. You will be able to make measurements. Okay, and so this is like that is shown. So for one direction you get one measurement, another direction you get another measurement, and so on and so forth. So when you fill the space, you get something of this sort. So each of these curves are basically what that you will measure. Okay, so all these curves will fill the three-dimensional fx, fy, z space of the object, and these are like surfaces. And once you do that, so the actual overall surface will be like the volume size of the volume will be 2k. So k from the input, k from the direction in which it is going. So it's a combination of the two that you will lighting. Okay, sure. Mhm. So you have a direction vector K coming in, like KP, and then you have a direction vector KS going out. Okay, so if you add the two vectors, so one way to think about these spheres is for any KP, you can have one sphere of the radius K, and for a different KP, you can have a radius K. For a different KP, you can have with the center here a radius K. Okay, so you put them all together. So what is the biggest length when they are exactly KP and KS are exactly aligned with each other? So this overall distance will be 2K. Right? So therefore, that's why this overall length will be 2K. So in essence, what I'm saying is that let me edit now this. So take any point here. There is a direction KP in which light comes in, and light scatters in all different directions, right? And so this Ks vector for any given one single Ks vector, light has scattered in this direction. So this it will be like a two-dimensional surface, which this is what this will be the two-dimensional Fourier transform of the image that you have measured. Okay, take the data you get, do the 2D Fourier transform. That data will be pasted along this curve, proportional to that after some proportionality constant. We'll do this. And for a different direction, different KP vectors, you will do the same thing. For a different direction vector, you will do the same thing. And you fill so slowly for a different direction, you will fill. So you will fill the Fourier space in 3D by collecting the data and putting it in the Fourier space in all these directions. Okay, and then again the same kind of like issue will be there because it's not uniformly distributed at all different in the Fourier domain. So it's much more intense in some places related to the others. Therefore, you have a filtering operation. So 1 over so the filter in this case is yeah. So the filter in this case is this e to the I or e to the minus j k d by 2jk. Okay, so that's the filter that you will have to use again, and that's the scaling function. And once you do that and once you fill this up and multiply by this filtering function, then you take the inverse Fourier transform in 3 dimensions, and you will get the overall structure of the refractive index, structure of the object, which is the distribution of refractive index at any given location. Any other questions? Okay. Yeah. So this is the essence of the inversion of diffraction tomography. So this is basically how the entire process works. I'm sorry. What do you mean? How could it's computational? Oh, so this is related to the spherical wave. So um, oh, so you have e to the j k dot r, right, divided by r. So this is the equation for a spherical wave. You take the Fourier transform of this. This is in the xyz domain, right? So if you do it in the kx domain, you'll get a filter. Uh-huh. Mm-hmm. Mm-hmm. Yeah. Correct. Ah, so it is so that is so for any point emitter, as you go farther away, it becomes less and less intensity light, right? So you have to undo the effect of this. So if you make a measurement from far away, you have to correct for the fact that it has traveled far the distance, and that's essentially so this light propagation is essentially accounts for that. So how much of light has propagated, how much distance, if you say in the Fourier domain, if you think about what happens, that's essentially the filter. So the filter is the Fourier electron. In the Fourier domain, that light propagates. Like it's basically of the form e to the I k z j k z z. And so, like yeah, so that will tell you from one plane to the other when light travels, what happens to the light. In the, so we saw the Fraunhofer and Fresnel like approximations and how if you have in one plane, light travels and you can figure out the field in another plane. So that's essentially this. So like, in the Fourier domain, you multiply by this k of h of k, 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 y, and the process of propagation is defined by this equation. Okay. Okay. So this is about diffraction tomography. The last thing I'll talk about today is another kind of localization, which is called interferometric localization. Okay, so there are this in fact like lends us to the idea of an instrument which uses is called optical coherence tomography, which is one of the instruments that I work on extensively in my lab. So the basic the foundation is as follows. So it uses what is called an interferometer. So let's say we have a source of light, something like a laser, which has one wavelength, which is monochromatic, one color, monochromatic light, and it's a coherent wave, meaning it's a wave which has the properties, it's a sinusoidal wave which is traveling. Let's say that's the nature of this particular source. Okay, so now let's say that we have a source of light, like so, like bring the light, put it on a beam splitter. So beam splitter is an object that splits the light into two pieces. So one part of the light travels down this way. If the light comes from the source and comes downwards, one part goes down, one part goes to the left. So one goes in this direction, one goes in this direction. And now you put a mirror over here, perpendicular to this beam. So this is a mirror, and you put this mirror on something with a stage or something which can move from like along this direction. Okay, that's the experiment that we were thinking about. So put this mirror, light from here comes, sorry, light comes and reflects back towards the beam splitter. Similarly, light comes in this direction, in on the other side, put the object that you are trying to image will be on this other side. So this is called one arm of the interferometer. So this process of splitting light and then combining it back is called interferometry. And so you have light incident on the beam splitter, split it into two. One goes to the sample, one goes to this mirror. Light comes back from here, light comes back from here, and at the beam splitter again, light that is coming back here, half of it will get reflected this way, and the light coming from the mirror will get half of it will get transmitted this way. Some of the light here will go back towards the source. We are not worried about that. We ignore what happens to that. But you put a detector on this side of the interferometer. So this is essentially called a Michelson interferometer. Albert Michelson, who was a scientist from a long time ago, he got a Nobel Prize in the early 1900s for inventing this approach. He was not doing imaging of any sort, but he was this this concept of interferometry is extremely sensitive. And it's so sensitive that, like you might have heard in the news a few years ago, they measured gravitational waves, literally waves from somewhere far away, from distant kind of across the universe, like waves came in. So this LIGO, where like they measured these kind of like gravitational waves, used an interferometer, something of this sort. It's much more sensitive that produces stabilization and like it is very precise and remarkable feat of engineering. But basically, the crucial thing is that this interferometry can be very sensitive. And so you can make very precise, very accurate measurements with this kind of approach. Okay, and we will use this for biomedical imaging. There are lots of different applications which this is used for. So the basic idea is you split the beam into two, like something happens to one beam, something else happens to the other beam. You combine the two and then put it on the detector, make a detector measurement, and then move this mirror and make a sequence of the detector measurements. From the signal that is detected, you can figure out something of what is going on inside the sample. From the interference pattern that you see, you can infer something about the what is inside the object. That's the basic idea behind this interferometry. So in the case of, if you have a source of one wavelength, monochromatic wave, which is coherent, which comes in and falls on this interferometer, then as you move the like a reference mirror, this is called the reference mirror. If you move the mirror from one end to the other, and you make, like you plot it as a function like on the x-axis, then the signal that you will detect, because of the interference of the beam that comes from the mirror and the one that comes from the object, will look like a sinusoid. Okay, it will actually have the same kind of shape as the light source. Okay, so basically, so that is like sort of, this is called an interferogram, or an interference pattern that you measure. And what does, how is this related to the object? It turns out that this object here, you can think of it as a reflector, just like you have a mirror here. This one surface of somewhere inside the object is also acting like a mirror of some sort, a weak mirror, but like something that reflects or scatters light back. And so you can, so depending on the position of this mirror relative to the position here, you will get an interference pattern. As you change this mirror, the distance here minus the distance here, the difference in distance is essentially what you are measuring or what you are plotting. So for example, the intensity that you measure is proportional to, there are some constants here which depends on the reflectivity, but more importantly, it depends on the time delay between this and this. Or in other words, the time is proportional to distance, because speed of light in air is constant, and therefore this distance minus this distance is what we are measuring. So in other words, this is a way of measuring distance, okay, and measuring depth. That's where we're going with it. Okay, so right now we have an interferogram. We don't know what the depth is, but here is the second trick. Instead of having a light of one wavelength, if you use a pulsed wave, where light of all multiple wavelengths, you make it a pulse of this shape. That is your source. Okay. Then, if that kind of a pulse is incident, the pulse splits into two. One pulse goes this way, and this the light goes this way. They recombine, and then you have it on the detector. As you move the reference mirror and make a measurement, you will see a pattern of this sort. This pattern is similar to the pattern of light, that the pulse of light that has come here. And so basically you will have a maximum when the mirror, the distance between the beam splitter and the object, like where the reflection happens or scattering happens, exactly matches the mirror position. The distance between the beam splitter and the mirror, if it's equal to the distance between the beam splitter and this sample layer here, if they become equal, that is when you have a maximum. And therefore, you have control over where the mirror position is. And if you know the mirror position, you like although you can that's the same as where the light is coming from, how deep it is. So this gives you a way of measuring depth, where how deep this is. Because you know the mirror position, that is the same as this how deep the signal is coming from inside the object. So you have a depth measurement. And of course, then you move the sample around and different positions and get a depth at every position, and that way you can get the three-dimensional structure of objects. That's the we'll get to that in another lecture, but I wanted to start with the basic principle of operation of what's the idea behind this. Okay? So it turns out that so in this case we said we need a pulse of light of this shape. You can create a pulse of this shape using what's called femtosecond lasers. There are ways of doing this, but those are expensive and not very easy to do. It turns out that even if you have what looks like a wavefront where it's low coherence, meaning there is no clear phase relationship between different wavelengths. But the important thing is there are not just one wavelength, but a bunch of wavelengths together. If you have a range of wavelengths of light incident at the same time, each of these wavelengths may not actually be there may not be a phase relationship between one wavelength and another wavelength. They are all completely independent of each other. For example, an LED source or any light bulb kind of a source, it emits light at this probably is an LED. This is white light, right? So it's emitting red color, orange color, yellow color, green color. All colors of light are being emitted by the simultaneously. But all these red and orange and yellow though are completely independent of each other. There is no phase relationship between one wave and another wave. But even if you use this kind of a light as a source and you split it in two, recombine, and you make a measurement as a function of mirror position, then you still get the exact same pulse. Okay, so then by making this pulse and you looking at the maximum over here, you can figure out at what depth the signal comes from. Okay, and this is I'll go into more details of this in a class on OCT, optical coherence tomography. But I think now is a good time to stop. And in today's lecture we looked at several different ways of making tomographic measurements. So there are different approaches depending on the nature of the object, nature of the source, how light matter interaction happens. Is it an absorption process in an array? Is it diffraction process? Is it scattering? Is it this kind of a depth measurement through scattering from the object? So there are several different ways in which you could do tomography, and we'll continue this in the next